here today. The first talk is gonna be by Thomas Rothvoss, and he will be talking about parameterized linear formulation of the integer half, which is a joint work with Fritz Heisenberg. So Thomas is a professor in the Paul G. Allen School of Computer Science and Engineering, and also the Department of Mathematics at the University of Washington. His research interests are approximation algorithms, theoretical integer programming, and convex geometry. He received plenty of prizes. For example, the 2018 Delbert Ray Falkerson Prize and the 2023 Gödel Prize. His research is supported by an Alfred P. Loan Research Fellowship, David and Lucille Packard Foundation Fellowship, as well as an NSF Career Award. So the floor is yours.
All right. Yeah, thanks a lot for having me, Sylvia and others. So this is some joint work with my PhD advisor, Fritz Heisenberg. He was visiting Seattle for his sabbatical, and kind of presenting the outcome of this. Okay, so this is what integer programming. So what is integer programming? You have a polyhedron, and you want to, let's say, maximize a linear function over the integer points, the polyhedron. It looks like this. This is, as you all know, this is a fundamental tool in operations research. And there's some practical tools, some very powerful practical tools to solve IPs, for example, branch and bound and all the variations. So I'm more of a theorist, and I like to prove things. And there's a little bit of a problem that solving integer programs is NP hard. So as a theorist, what would you even do? So in theoretical integer programming, sort of the direction is often, what type of special cases of integer programs can you still solve in polynomial time? There's one that you may have seen even in some undergraduate class. It's if the constraint matrix of your integer program happens to be totally unimodular, it means all the determinants of square submatrices are either -1, 0, or 1, then you can actually solve the integer program in polynomial time. The reason why this is true is that, as you can sort of imagine from the picture, all the extreme points of your polyhedron, they happen to be integrals. You just need to solve a linear program. There's actually there's an extension of this question. It's in fact, if all the determinants of your constraint matrix, so the constraint matrix is integer, but the determinants are upper bounded by some constant delta, can you still solve the problem, the integer problem in polynomial time? So a very popular open question. It seems to be a lot less trivial. Particularly, as you can imagine from the picture, the vertices of the polyhedron are not integer anymore. There's some progress for special cases, but not the general one. All right, so but this is not actually the direction in which I'm going to go. There's a different direction about sort of special cases of integer linear programming, and it's the one where the constraint matrix A is extremely sparse, or to be more precise, the support is very limited. Here's a variant that's called n-fold integer program. It's an integer linear program where more or less the constraint matrix, it has some small blocks on the diagonal. These are k by k blocks. Think of k as being a constant. And additionally, you have a number k of joint variables, and you have a number k of joint constraints. So in other words, after deleting a number k, again constant, of variables and deleting k many constraints, your integer linear program would actually decompose into disjoint IPs. So what's known about this problem is that well, it kind of can be solved in polynomial time, but things are less nice here. So the running time is more into some number that depends on that parameter k. It also depends on a parameter delta, which is the largest entry in the matrix. Okay, so this is work by Hammaker and Weismantel. Popular question here is whether one can move that dependence out of the exponent and in front of the n. So whether there is some universal exponent for the n and some maybe very ugly function in front. So this is the question: can you solve these n-fold integer programs in fixed parameterized time, where the parameters are the size of the blocks and the largest entry in the matrix? Okay, I've been talking for a while. Is there any questions so far?
I don't see any questions in the chat. So,
okay, thank you. Okay, so well, this question about the FBT-ness, this is open. There was a very nice paper that I liked a lot by a couple of authors, and I'm not sure how to pronounce this, Cslovjecsek et al. So what they proved is that there's a special case of this n-fold integer programming where you don't have these k constraints that connect everything. And they actually could prove that this type of IP you can solve in FBT time. This IP where you don't have the joint constraints, this is also called two-stage stochastic IP, because you could imagine that there are these k joint variables. Once you fix them, there are these n disjoint blocks of variables, of k variables, that you then need to solve in a second phase. So you can think of this as a two-stage integer program. And they actually could prove that you have an FBT time algorithm where the nasty dependence on the coefficient is only in the coefficient of the second stage blocks. It does not depend nastily on the first stage, the coefficients. Okay. They actually proved kind of a general statement about the kind of the convexity of integer cones. And the way they proved it, they couldn't handle an objective function in there. And this was our motivation. This is where our work started. And so what Fritz and I are to prove is that you can also solve this problem within the same running time with an objective function. But the way we prove it is actually more of a geometric statement that doesn't really look like it has much to do with this. All right. So let's go to the geometric statement that we were then following after this we were interested in. Let me start with what's called a cutting plane. All right. So let's say you have a polytope P, and you take an integer. Sorry. You look at the convex hull of all the integer points in your polytope. This is called the integer hull. Now, let's take an integer direction C, and the right-hand side does not have to be integer. But you can imagine that you could run down the right-hand side. So you would cut off some points of your polytope, but you wouldn't cut off any integer points. And in particular, you wouldn't cut off any points in the integer hull. Okay, so this inequality Cx at most delta, this is called a atal-Gomory cutting plane. Now imagine you take all possible atal-Gomory cutting planes and you throw them in simultaneously. So the picture looks like this. These are maybe all non-redundant cutting planes. All of them you shift in until the right-hand side that's an integer. And then the object that you're getting, P prime, this is called the elementary closure of P. So this is an intersection of all the Gomory atal cutting planes. As the picture indicates, in general, what you're getting is something that's strictly between the original polytope and the integer hull. In particular, it's not necessarily true that the Gomory-Schwartz closure is already your integer hull. Okay. Good. So in general, you should not think about this as a theoretically efficient procedure. It's in particular checking whether a given point is in the elementary closure is co-NP hard. Okay. Anyway, but you could imagine you could iterate this procedure. So you could take the elementary closure of the elementary closure, and so on and so on. And so after I many iterations, what you get is the ith closure. I don't have a picture. So the limits of my drawing skills.
Before we continue, there is a question.
Oh yeah, please.
About the previous slide, when you were talking about the function f in the time complexity term. Yeah, exactly. They're asking like what type of function is f. So I guess like a polynomial or exponential or something.
Oh, exponential. In fact, so their function f, the one by Cslovjecsek et al., it's double exponential.
Okay.
Ours is triple exponential, but it's
in
yes.
K and in delta. So okay, in both of them. Okay. So I hope this answers the question.
Yes, it's a little. Is this practically relevant? Maybe debatable, because you're really allowed to like shovel everything into that function.
Into K. Yeah.
Good. All right. So we were at the ith elementary closure. You can actually prove that for actual polyhedron, there's a finite number of times that you need to apply this closure operator until you reach the integer hull. And that number of times is called the Schwartz rank of your polyhedron. There are some bounds on how big that Schwartz rank is. For example, if you're in n dimensions, then it's it can be the upper bound that is known as exponential. Okay, so again, we have a procedure where you need to throw in probably exponentially many inequalities, and you need to iterate this exponentially many times. So again, maybe not an efficient procedure. All right. Okay. So here's the geometric fact that I wanted to get at. Let's look at a polyhedron P, and let's think of this polyhedron as a function of the right-hand side. And let's imagine how actually would not only the polyhedron, but its integer hull change if I was to change the right-hand side. I have a very simple example in 2 dimensions where I'm only going to change one of the coefficients on the right-hand side. So I'm going to move out the coefficient on the right-hand side, and you can see in green how the integer hull changes, and it kind of, you can probably see that one thing it does not do is it does not change linearly. So it does not seem that the constraints, the right-hand side constraints of the integer hull change linearly in the right-hand side of the original polytope, because there's this discreteness. Okay. But maybe you could imagine if I would change the right-hand side always by some large coefficient, which is, let's say, a multiple of all kinds of other coefficients, then maybe I do have a linear. It's a bit of a vague statement, but this will turn out to be true. Okay. So if I would change my right-hand side B by vertices from a very sparse lattice, a certain very sparse lattice, then actually the integer Hall will change linearly in B. This is the thing I want to prove. Okay. All right. So we found it very hard to directly argue using the integer Hall. And it ended up being a lot easier to argue about the Gomory-Schwarzschild closure. And that should be enough, because if you can prove something for the Schwarzschild closure, then you need a finite number of iterations of the Schwarzschild closure until you reach the integer Hall. So whatever you prove for the Schwarzschild closure might also apply to the integer Hall. And that is our proof strategy. All right. Okay, good. So let's look at a polyhedron P, and we think that it depends on the right-hand side B. And let's discuss how the Schwarzschild closure looks like. All right. So any inequality from the first closure, it's obtained as follows: you take some non-negative multiple of the right-hand side of the left-hand side constraint matrix, so that you get an integer, and then you basically round down that same coefficient vector lambda b. You round it down. This is one of your cutting planes. And now you can start reasoning about the vector lambda. You can discuss that actually. It should be between 0 and 1, some number between 0 and 1. If it was bigger, then the cut you would get would be dominated by others. You could reason that the support is at most dimension by Theodoros' theorem. Something very important is actually that the vector lambda, it's kind of obtained by solving a linear program itself. So it must be rational if A is rational, and in particular, by Cramer's rule, the vector lambda will be some integer multiple of some subdeterminant of A. Okay, so if we pick D, capital D, as a multiple of all possible subdeterminants of A, which is going to be some giant number. In fact, it can be double exponential in the coefficients of A, at the dimension of A, then lambda will be an integer multiple of D, 1 over D. Okay. Now, if we look at our Gomory-Schwarzschild cutting plane, and let's say we fix the remainder of B modulo this number giant D, this giant D number, then we can pull out the remainder, and so the difference, so lambda transpose times the difference between B and that remainder, that's going to be an integer. I can actually pull it out of the flooring operation. Okay. And now if you look at this, then what this says is that for one constraint of the elementary closure, if I vary B, but I always pick B so that mod D, it's equal to the same number R, to the same vector R, then actually the right-hand side is linear in B. And that is everything, because this means that the right-hand side for one constraint of the Schwarzschild closure is linear in B if I pick the vectors in this always mod D being the same. And now you just iterate this a finite number of times, Schwarzschild rank many times, and you get the same statement for the integer Hall. There's a bit of a mess. Keeping track, there's some inductive proof, and you need to keep track how all the parameters are growing. Well, that's it. That's the whole idea. Yeah. Okay. If you write out the full statement, then all right. Yeah, this is what I said. Then the theorem looks a little bit messy. There's like an order of quantors. But the statement you would get is as follows, that Well, you can take any polyhedron. You have some integer constraint matrix. Then you can actually write the integer hull of your polyhedron dependent on B in this form, where the right-hand side is linear in B plus some offset, which only depends on B modular that constant D. Okay. And again, if you do the math, then what upper bound on D do you get? Earlier I said double exponential, but then there's this induction, and then it ends up being triple exponential. So this is not a pleasant number. I don't know. Okay. So this is the main technical theorem, which basically I've shown you the proof, modulo technical details that you need to have worked out either by a busy graduate student or by a PhD advisor on a sabbatical. So it's okay, but now let's see what we can actually do with this. This is a theorem which gives you a triple exponential bound on something. Okay. All right. So let's go back to this two-stage stochastic integer programming problem, which looks like this. Again, there is we have a bunch of integer variables, a bunch of blocks of integer variables. Again, k is a constant. So there's some joint variables x, and then once you've determined x, there are these disjoint problems where you need to pick a vector, a block of vectors x, y. Okay. So you can imagine that you can rewrite this constraint, and you can write the set of feasible solutions yi that you can pick after you have picked x. It's a polyhedron where the right-hand side depends linearly on x. But the problem is you need to pick an integer yi. Okay, so far you have only integer variables. Right? Now with this polyhedron, I can say instead of a polyhedron, I take the integer hull of that polyhedron. Since I have to pick an integer vector, I don't change anything. And now, well, if I think of my number, the block size k as a constant, and I think of that parameter delta, the largest integer in A, as a constant, then I can actually guess the remainder of the optimal solution x mod d. And I can modify my IP, and I say I only look at x that are r mod d. And after this, you actually know for every I, you know that right-hand side here, what it has to be mod d. And after this, you can actually replace this integer hull. You actually know what the integer hull looks like. You can explicitly replace it. And after this replacement, you don't need to enforce that the yi is integer. You can just make it rational, real. Because if you compute an extreme point to this mixed integer linear program, then all the yi's, there will be extreme points of this thing on the right-hand side, and this is the integer hull. So the extreme points will be integer. You don't need to enforce the integerness. So the only variable block that you need to force to be integer is x. So you have a mixed integer program with k constantly many integer constraints. And this you can solve in polynomial time times some ugly number dependent on k. And that was it. I think I'm kind of out of time, but I have a few open problems that I can mention. So the mod d that we get out of our theorem, it's triple exponential. Double exponential would be the more natural bound because, well, the least common multiple of all subdeterminants of a matrix A, it can in fact be double exponential. So double exponential is our guess what it should be. And we still don't know how to solve these general n-fold IPs in FBT time. N-fold IPs, they have these joint constraints. So we don't know how to handle these joint constraints additionally. And finally, if you have completely unconstrained and variable integer programs, the best known running time how to solve those is in log n to the n. Some work with my graduate student from 2 years ago. The conjecture is that a constant to the n should be enough, but we don't know how to do that either. So thank you.
Thank you very much for your talk. So the speaker will not stay that long for the breakout room. So if you have any questions, take advantage of it now. We're going to give you a few minutes for questions.
You can either raise your hand or type in the chat as you prefer. I do have a question. I can start maybe. So can you, for the case of the n-fold, I guess these problems with the complicated constraints, with some kind of like Lagrangeizing idea, but perhaps work? Or like if you have like let's say you just had one constraint or something like that.
Oh. Yeah, I don't know. Probably starting with one constraint.
Mm-hmm.
Maybe would make more sense. Yes. Yeah, I don't know.
Okay, and then maybe a second question is, so you said that the integer hull can change quite a lot, right, as you change b. But when you change it a little bit, does the set of, does it really change that much every time? Like, is it completely different if you change it a little bit and you don't change it by these nice factors? Maybe I misunderstood what that statement, but I guess it seems like you could reuse parametrically some of the cuts or some of the techniques, even when it's not quite in this nice integer multiples.
I see. Yeah, we looked at the exact case. Right. So I think you could, if you look at the statement here, I think you can upper bound on how big the FR, how big the offset is. So this may be partly an answer to your question, so that, yeah, I think you could prove something.
Xenia has a question too. Thank you, Thomas. Thank you very much for the nice talk, and thank you for joining us.
Thank you.
Yeah, hi, thank you for the talk. So my question is, well, actually a very broad question that might be a little bit beyond the scope of the talk, but it got me curious because I'm working on something maybe a little similar, but in the nonlinear side of things. And basically you are here working on identifying cases where things are a little bit more convenient. So when you have integer variables, and I do the same for non-convexities, and basically I just got a bit curious about whether maybe this can be combined, because actually that was one of my, or has been one of the questions on my mind, whether I can also bring the integer aspect into this question about the non-convexity and generalized convexity.
So you have a non-convex problem?
Yeah, let's say an MINLP.
And, yeah, I don't know. It's okay. So what are you looking at? Not at the convex hull of the integer point, because that's not the right thing.
Yeah, so in my case, I'm looking at basically when every looking for the cases when every local optimum is also globally optimal.
Interesting.
Yeah, I mean, I know it's a bit of a broad question, so yeah, but it's just get curious.
Maybe we have time for one last quick question from Matthias.
Yeah.
Or not necessarily quick, but one last question from Matthias.
Yeah, well, thanks for the talk. I guess if the say the x variables in the n-fold case, or here in this one, if these are bounded reasonably, like binary or so, then this enumeration of remainders is rarely better than just enumerating the binary solutions. Is that true? So it really pays off only in the general integer situation. Is that correct?
Yeah. If you tell me that x is binary, then well, there's 2 to the k options. So I could just guess what x is, and the rest would just decompose into disjoint problems.
Yeah.
Really, x being unbounded is the issue. Yes.
Yeah. Okay, thanks.
Thanks, Matthias.
Perfect. So thanks again to the speaker. And we will now go to, well, we will now start listening about the second topic.